We can wait a few minutes.
Yeah. But the streaming, it starts by itself, right? Yeah.
Там аккуратнее. Как не Stopp. Ja, det sa proprio il senso, non quando sono agitando, non sono troppo sono arrivato in
ora di streaming.
Ah, sì? Oh, no? Or we can wait 2 more minutes. Okay. Alright. Okay, the light's on off. The light, should we turn it off or go with it? Okay, that's okay. Okay. Hi everybody. Good afternoon. My name is Shubham and welcome to Deep Learning Paper Reviews. And yeah, so today we'll be looking at activity recognition. And yeah, first I would like to make it clear that yeah, so my accent is a bit different. If you don't understand something I say, it sounds a bit different to you, let me know. I'll stop there and repeat. And if I go really fast, if I speak super fast and you don't understand, let me know. Okay. So yeah, so the topic is activity recognition, and so these are the contents. We'll be going through this stuff. So we look at what activity recognition is, and then we look at the data sets used in this area of deep learning, and then we jump directly to the methods for it. So we'll be covering about 7 papers around, and yeah, so that's all. Okay, so there's one thing that, I mean, everybody uses the internet these days, and there are a lot of videos on the internet, and the videos are, I mean, so for example, I really like to go to YouTube and watch something, and when I do, something like this happens. So you're trying to see which Pokemon it is, and suddenly this happens. So you get rickrolled. So this is the thing that there are a lot of videos out there, and you don't know what's going to be inside. And the videos, these keep coming to the internet. So YouTube gets what, around 300 hours of video every minute, and that's just YouTube. There's also Facebook, and there's Instagram, and I don't know how many services. So the content is growing a lot, but the problem is when we cannot manually look at them and verify them. Is it okay or is it not? So we can use algorithms to do that, and yeah, so we'll be talking about the deep learning side of the algorithms for that. And yeah, so this is for recognizing some activities in videos. What is happening inside? Is it wrong it is right, or what is it. And the videos we have, so video is the data here. And so what we do in deep learning is we have the data, we have some model, so we feed the model some data, and then we classify or we regress or something. So this is actually a classification problem, which is activity recognition. There are also other fields around videos. So you can also, for example, what we had here was you could watch a video and describe what's going on inside it. And yeah, so but we'll be looking at classification. So what is the data like? So video it could be decomposed into two parts, which are useful to us, which is spatial and temporal. So spatial is the spatial part represents what scenes or what objects you see in the video, what you can see, and the temporal, like you can see what moments are happening. And yeah, so the task activity direction is actually just to classify. You take the data and you find a way where you can make the best out of the data to get a good prediction, and that's it. And so the applications for this, it's mostly surveillance or abnormal activity detection, or you want to monitor something like a patient or elderly person or what's happening there or anything. So yeah, so in this field, so what does the data look like? I mean, what are the data sets? Sorry. So data sets, these are the two main data sets. That's a UCF, a 101, and HMDB. And okay, here. So these are actually the main data sets for benchmarking, and there are more data sets with higher data, but this is the one people use. The most papers are using these. So for example, let's say this person is blow drying the hair, brushing teeth, cutting in the kitchen, something. So these are some activities happening in the video, and we'll be looking at human activities actually, because that's where the research is mostly. That's what I've seen. And there's another one which is HMDB, and here are what they have. So this one has around 51 classes, and the previous one has around 101 classes, and that's the number of clips and videos they have. So we actually have videos and we extract clips from them, and then we train on the clips. And these are the classes. We have 51 classes in HMDB. UCF has 101 classes. And then the third one is kinetics. Okay, you can't see. Let me fix this. Sorry. Nope. Yeah. No. Okay. Maybe now you can see. I'll go back to full screen soon. Don't worry. So yeah, we have clips, and so the third one is the kinetics dataset. Let's skip this for now. We'll come back to it later. But for now, the two main benchmarking datasets are UCF and HMDB. And yeah, what do these datasets look like? So these are the activities happening in, let's say this is UCF actually, UCF 101. So these clips are very short, not that long actually, and you can just extract some frames out of them, and then based on that you train a model, and then you predict. Okay, so that's what the data is, and now we go directly to algorithms, the deep learning side of this. So we'll be starting from 2014. So that's somewhere where one of the first deep learning algorithms came for this task, and then we'll be like moving towards to 2017 or something. So we'll see how this field is evolving. And so yeah, the first one was this one is kind of from a famous author, is Andrei Karpathy. And yeah, so their problem was they had this big data set of 1 million YouTube videos, which they wanted to classify. And so it's actually classification of videos, but in the end it goes towards activity recognition because the same things get used there. And so CNNs were also like pretty good at that time, and a lot of new models were coming, so they use CNNs because so videos are made out of what, frames, images, and CNNs are very good at extracting these images and like learning these features. So what the paper studied, how could you change the CNN? How could you change the temporal connectivity of the CNN, so it could also make some sense out of the order in which the frames are appearing, and also how much does motion help in like classifying these images which have come from video. So the main thing they did in this paper was they came up with these four architectures. So there's a single frame where you are just classifying a video based on one frame out of it. So let's say a person is brushing their hair or something, and so the model recognizes a hairbrush, so it might be able to say it's somebody brushing their hair, or there's hair or something, so it can relate. But maybe the hairbrush is lying in the background and somebody is doing something else with there's also hair and some other activities happening, so that might be wrong. But yeah, so that was single frame. And then there is late fusion, where they have so this is the bottom actually where you feed in the data, and so they feed in two images. First image goes in, there's like a tower of there's a stream of convolution and yeah, pooling and stuff, and then goes to fully connected, and then another frame is fed, which is 15 frames apart, and then that goes through another stream, and then they get fused at the last layers actually. So this is somewhat like let's say there's a person, he looks kind of angry, and his hand is kind of charged in the air, and then in the next frame you see this person's hand, which is like not charged now, it's away from his face, and then another person's face broken or something. So probably he punched somebody. So that was the activity. So based on that, can you guess what activity is happening? So that's what this model is supposed to do, I suppose. And there's early fusion. So in early fusion, you feed like probably, I think, yeah, 10 frames, 10 consecutive frames to the first model, and the first layer, first convolution layer, and then you move towards fully connected, and you try to guess what is happening there. And in slow fusion, you have four parallel, let's say, yeah, four parallel convolution layers, and then you aggregate a few of them, and then later at another stage you aggregate more of them. So this is what they tried, and how it went was like this. So if we look at the results, so yeah, let's actually remember the name. So there's single frame, late fusion, early fusion, slow fusion. So no, here, yes, no, yes. Okay, so single frame gives somewhat 41% accuracy, which is kind of strange, and still good actually. You can guess a lot from a single frame. And early fusion, where you are mixing up multiple frames in the first layer, it gives around 38.9%. What does the best is slow fusion, which was this one. It performs the best. So they go with this model, and then they actually pre-train it on sports 1 million dataset, and then they go to this benchmarking dataset, UCF 101, and then they report 65.4% of accuracy.
How many classes are used in this dataset?
Which one?
In
Sports?
Yes.
It has 487 classes. And yeah, but they say there's a lot of noise, and also it's actually not used as a benchmark because they say it is not annotated by humans, it's machine annotated. So probably that's why there's noise. And yeah, so
And what is this single frame plus multi-res?
yeah, so this is another thing they try. I kind of skipped that because it never got built upon. It kind of failed in this paper, and nobody built upon this. So they have another model where they look at the image at the center of the image, and then like a small center crop, and then the whole image also, and then they fuse it at some point. So it does something like this here.
But it seems to be the best in this table if I'm not correct.
Yeah, but then later papers, they don't care about it at all. So yeah, but then also anyways they go with slow fusion and they do this. So yeah, so we have 65.4% accuracy with slow fusion model here, and then there was okay. So we can look at some results, which is pretty nice. So looking at this one here at the right bottom. So this is like some pool table. I don't know the sport, so I would just say it's pool. But they so the ground truth, it says the blue thing is ground truth. It says it's 8 ball, but there's 9 ball and all these things predicted. Sorry, and it's supposed to predict 8 ball here actually. So I mean it brings up all these similar classes, and let's say like looking at arena football. So it's supposed to predict this is arena football, but I don't even know how it does this. Maybe it looks like in American football to me, like rugby or something. So it's kind of close enough, I would say. But some things it does, like for example, long putting predicts perfectly. and this ultra marathon also. So yeah, so it does learn something though. Okay, so moving on from that, like another paper came up, this was by the authors of VGGNet. So it's called two-stream architecture, two-stream CNN. And so what they point out is that feeding just RGB frames to a model is not enough to capture emotion inside it. Maybe you recognize objects, but not the motion so well. And so they use the late fusion technique, not slow fusion, what worked the best, but late fusion, this one, where you feed something here, and fuse it later. And yeah. So they also take inspiration from the human visual cortex, which they say it has, they cite that it has two pathways. One is like a ventral stream, which recognize the objects, and the dorsal stream, which recognize the motion in what we see. And yeah, so they propose this two-stream architecture. One is, so they have a spatial stream and a temporal stream in it. And yeah, I'll actually show it. So this is the architecture what they propose. And yeah, so this is like a image classification net, which takes in a single frame. It looks what objects are present, and this one takes the motion information, which I'll tell you what it is, and predicts something. And at the end, they fuse together, and yeah, maybe average, or like, yeah, they use SVMs or something there and classify what action it is. So this spatial stream is actually just a ImageNet trained model, which can recognize objects or something, and it's kind of fine-tuned on these what do you say? Yeah, the data sets of this field. And the temporal stream. So the temporal stream actually takes optical flow images. So for example, these are two frames, the consecutive frames. You feed this to an optical flow algorithm, and it gives you a displacement field like this, which says, there's a way of looking at it actually. These are the fields. So it says there's a motion going that direction where these vectors are pointing. So this is like the displacement field on the x-axis, and this is the y-axis. So this is what you use as input. So you feed this to the the temporal stream, and you feed 10 consecutive frames. So you know what motion is happening, and you have also recognized what objects are there in this particular video, and then you fuse it together. So yeah, the problem here is they're able to like have a pretty good classifier with the image part, but the temporal part not so much, because the data is not enough. So because you have ImageNet to pre-train a model and learn these image features for sure, but temporal there's nothing to learn optical flow from. So what they do is they do this multitask learning. They mix up these two data sets, and then they learn together on the training side, and then they use it together. And yeah, so they report around 88% accuracy on UCF, and HMDB around 59.4% accuracy. So we're gonna see this like better accuracy on UCF and bad accuracies on HMDB, but I mean they'll improve eventually. But it'll be bad because the data in HMDB is super less. So is, yeah, not that much, and UCF also doesn't have a lot of data. So yeah, so this is what the two-stream architecture does. And then there's another, so there was next, this was in 2015, some paper from Facebook, that use of 3D CNN would be much better. So what they notice is that if you use a 2D convolution or to capture motion between frames, it's not enough because you're losing motion. Why? Because if you look at this image, what a 2D image or 2D convolution does. So if you have one image incoming and one kernel, so you slide this kernel throughout the image, and then you get one channel output. Now you have multiple images coming, and you also have one kernel. So the concept remains the same. This kernel is applied to all these images, and then in the end you add up, and then you get one output again. But in a 3D convolution system, what you have depths in the kernel. So the same kernel doesn't get applied all together to all the frames. It has a depth of, let's say, 3 images, 3 frames. So this kernel will only slide towards these 3 and then produce one kernel. So in the end, it'll produce a volume. So it kind of preserves the motion to some extent. So they also say like gradual pooling in the time and space dimension will help in learning better features, because if you just pull everything in the first layer, you might not send what you want to learn to the next layer. And yeah, so they form this 3D CNN, and they form a simple like sequential architecture. And yeah, so this is actually kind of learned from, I mean, it's kind of inspired, I mean, it was 3D convolution is nothing new, it was been done before, but they also relate to the slow fusion method, which is this one. So you gradually pool the features and then you, yeah, classify or something. So yeah, what they did is they used this, I mean, VGG architecture, I think, where they had like the kernels of 3 by 3, but then the kernels also had a temporal depth of 3 again. So it was 3 by 3 by 3, and with a stride of 1 by 1 by 1. And also in the first layer, they wouldn't pool in the temporal direction. So to preserve these features, they will pool only one channel, and then later on they will pool, yeah, do a 2 by 2 by 2 pooling things. So they also added like padding in the temporal dimension, and yeah. So one thing to notice here, one thing to remember, we'll come back to this later, that same temporal depth is applied throughout the network. So the entire network is operating on the same depth, and they also kind of report that it works well for them. They try it out, and just the same thing works better. But yeah, so looking at the results, so they report with a single net, they report 82.3% accuracy, which is less than 2stream. Actually, 2stream reports some 88%. But yeah, in the end, if you use three 3D convolution nets together, so this IDT is a classical feature. It's not based on neural nets. So it's like a feature they add. So it's called independent dense trajectories, improved dense trajectories. Sorry. Yeah. So with that, they get around 90% accuracy. So yeah, this was 3D convnets, and then some other paper we have. Yeah, so 3D convnets kind of stopped there. There were some improvements later, but nobody used it for some time. And the two stream networks, they kept going on. So this is temporal segment networks. So it's kind of a framework they use to improve upon the two stream architectures. So they use the two stream architecture there, but they use other things around it. So you can, so this is actually, I mean, people use it even with the newer methods to improve their method at some point. So yeah, so what their point is that the problem here is we are not able to capture long-term range temporal motion within the videos, and they also say that if you are taking up the concurrent like consecutive frames, it's kind of redundant information. So there's not much motion in consecutive frames. But actually, so let's say if you look at this image here, so this is one snippet. So one snippet is just one clip going inside. Previously, we were just taking this much information and predicting something. So if you look at this, there's a woman running there. So I would just say, I mean, I think the net would also say that it's a running activity. Is quite possible. But then if you look at other snippets from the video, it's actually she's running, and then there's a high jump happening, and so that could have been missed there. So what they do is they use this partially sampling technique. Instead of sampling anywhere from the video and taking up a RGB image and optical flow from there, they do this sparse sampling, and they take multiple segments from the video, and then they run it through the temporal network. And then there's a consensus function, which is they try different functions, but the averaging works the best. So they average out the predictions, and then they calculate the class probabilities, whatever, like based on these multiple segments from the same video. And it's also run through the same network actually. So they do that, and then if there's a mistake, so they backpropagate based on all three segments, and then the weights are updated. Yeah, so that's how this one works. So every snippet gets its own prediction, and then the consensus function is there, and they have probabilities. And yeah, so more things they introduce. Yeah, so they also point out that the k, you can fix the k is the number of segments. So for example, here it was 3, and they also use 3 in the best model of the report, I think. So they say you can fix this k as 3, and you can also reduce the number of snippets. So it kind of helps with the computational cost, because then you're not using a lot of optical flow, and yeah, you're predicting Yeah, iterating quickly. And other things they introduce is use of a deeper network. They say it works better. And so they also introduce this thing called a warped optical flow is another algorithm, because so we'll see a lot of different algorithms of optical flow. Everybody uses their own and they say this is better, that is better, but not much difference in the end. So they say use of warped optical flow as additional modality. So as a modality they mean using another third stream, so that would add another network to it. And so here are the results actually. So they come up to, in UCF dataset, they come up to 94%, and with this third mortality, they come 0.2 more. So that's the only improvement. But maybe since you're in the 90s, it's kind of a big improvement. I'm not sure. But nobody actually uses the third mortality in the other papers. They only cite this two modalities part. And yeah. So also another thing they introduce is cross modality pre-training. So this is previously we had this problem of we were not able to train these temporal network with anything because there was no data set. So what they do is they try to use a ImageNet data set here. So for that, first of all, they scale, so they discretize the optical flow images to between 0 and 255. So they look like probably, I mean, they feel like images from the data structure. And then they alter the first channel, because a regular image model would have RGB channels, 3 channels, and in optical flow we might want to give in 20, what do you say, yeah, 10 to 20 frames together. So that wouldn't be possible. So what they do is they average out the 3 channels, the weights in these 3 channels, and then they scale it to 10 or 20, how much ever you want, and then normalize. And then so the first layer is altered, and then it's kind of fine-tuned. So that's what they introduce, the use of a pre-trained network. You can and kind of increase the like accuracy based on that. So yeah, so TSN goes up to 94, 94.2. I mean, sorry, yeah, with UCF dataset, and with the HMDB dataset goes up to 69.4. Okay, so this is another one. This is it's called hidden two-stream CNN. So this paper they call like scoring higher accuracy on datasets another line of work. They say what they want to do is they want to make the process more optimal, and currently it is not very optimal because it's not really end to end. That's what they point out, because you have to take a video, you have to pre-compute the optical flow already, and then you have to feed in the optical flow, which is, yeah, took some time to pre-compute. You hardly used memory for that, and yeah, and then you given the image and that goes inside. So they point out it is time consuming to use optical flow, and also computationally heavy and storage demanding, because a lot of data sets, when you calculate the optical flow, it gets to about 27-30 gigabytes of data in the end. And yeah, I mean, that's just a small data set actually, and there are still big of data sets to deal with. So yeah, so they introduced this network called MotionNet, and this MotionNet is actually it's a image reconstruction network actually. So what it does, it takes these consecutive RGB frames inside, and it predicts optical flow frames from it. So you're able to just feed RGB to it, to your network, and it predicts optical flow by itself, and then passes on to a temporal stream, which was also in the previous ones. So this is still the two-stream architecture being carried forward, but with this addition of calculating optical flow on the go. Sorry. So yeah, they have this terminology that this is MotionNet. This one stacked with a temporal stream together is a stacked temporal net. Let me see. Yeah, stacked temporal CNN. And then if you have a parallel thing together, you call it hidden two-stream CNNs. And yeah, so another good thing, I mean, interesting thing they introduced is how to train this MotionNet. So like the usual way to train any network is supervised learning, because you would need ground truth data and you would need data to do that. But they point out that if you use ground truth data with anything, so the net becomes biased towards this data set exactly, and it would only work well with this data set, and wouldn't work so well with other data sets. So what they do is they bring this, yeah, so they introduce this unsupervised way of training this network. So they call it an image reconstruction problem. Okay, so let's say they give these two images. We can actually look at this, so let's say there's MotionNet and we give it I1 and I2, these two images, and it constructs this, let's call this V. This is the optical flow we want to compute, let's say that. So it constructs V, and they have this inverse swapping function, which accepts I2 and V, and it helps you reconstruct I1. So based on the original I1 and the reconstructed I1, so your job is to minimize the difference between the original and the reconstructed I1 image, and that's how you optimize the network. So they actually use like three different yeah, so they use these three different loss functions to do that. I haven't listed them here because I actually don't understand them so much, because more from image reconstruction side of deep learning, I'm looking into that. But yeah, in the end it works well, and also you don't need ground data for this. So that's one nice thing they introduce. So let's see, yeah, just a second. How do I scroll? Yeah, maybe you can see it here. I don't know. Never mind. I'll just say it. So yeah, so they are able to. The good thing, I mean, they don't beat the accuracy so well, but they beat the FPS somehow. So two-stream CNNs, they say it takes 14.3. It gives 14.3 frames per second, but they are able to compute these things at 120 frames per second. So it's quite faster, and the accuracy they is 89.82. So this, oh sorry, it's not that. Let's not look at that accuracy, because it's on the first split of UCF. This is the accuracy they report. So they use this. Yeah. So this is they report 90.3% on UCF and 60.5% on HMDB, but with the use of TSN, which is, you can put TSN around any two-stream network probably, and you can reach up to 93.1%. So like this paper kind of says that you might not need to pre-compute optical flow. And yeah, so there was another paper called inflated. So it's not called this. It's called actually. It's named on this movie called Quo Vadis. It's some movie in 1951. So they introduced this new model, and they use this new dataset called kinetics. So this dataset and this paper both are actually from DeepMind. So this dataset looks like this. So yeah, they also, I mean, they address there's a lot of lack of data. That's why we're not doing that good in this field. So we need better data to understand these things. So this dataset is this one. Yeah, so this is what the dataset is like. So it has around let me see. It has 400 classes, and in every class there are more than 400 clips, and there are 240K training videos, and in overall I think there are a lot of videos. So let's see. So these are like 50 classes. So let's look at like moving lawns, and yeah, so they have a lot of these variations and more variations and more. For example, this is some lawn moving, and also let's say this is another kind of lawn moving. So your model gets learned a lot, and so these are actually just one clip taken from one video. And also another good thing to notice is these videos have a lot of camera motion. So previously, if we look at these videos, or let's say there's barely any camera motion, so maybe the model doesn't learn much. Maybe the model just takes some background as foreground, something happens. So that's something good about this dataset, and it's pretty big. Okay, so this dataset is introduced in this paper, and also so they introduce this thing called inflating a 2D CNN model into a 3D model. So like if you're using a 2D CNN, the regular ImageNet model, we can use the weights which are from ImageNet totally, but in a 3D model you cannot, because there is no pre-trained 3D model available, or you will need to do it by yourself. So what they do is they propose copying. For example, there's a 3x3 kernel which is pre-trained, so they copy it 3 times in the temporal depth, and that's what they call inflating. So the every model is copied in the temporal depth, and they sort of inflate the model. So this actually, it's an inception module image, and yeah, so it was supposed to be 3x3, but now it's 3x3x3 because these models are just copied. The frames, I mean, the kernels are just copied. The weights are all inflated. So that's one way of so they use that with their model, and also so they investigate all the previous models that have been tried, and and they also try out the new, like pre-training them on the new data set, and then they propose a new model for themselves. And yeah, so their new model is actually it's inflated two-stream architecture where both the streams are 3D now. So both the streams accept. So there's one network here which accepts 1 to k. So let's say, like, yeah, I think it accepts 64 frames. Yeah, 64 frames of optical flow and also 64 frames of RGB images goes into a 3D coordinate, which is sort of inflated on ImageNet data, and then it's fused later, like late fusion, exactly like two-stream, and then they benchmark this stuff. So yeah, and what the results they report is, so okay, how does this go away? Okay, so you can't barely, okay, maybe you can't see, but actually it would be nice if you can see, so we can just put it here. Yeah. Okay, so the LSTM, we didn't discuss that, but it's a very basic model, never mind. Yeah, so 3D coordinate, originally they get, I don't know why they're not able to regenerate the results what previous papers did. So on UCF they report 51.6%, and with two stream they get 91%, and this is the original what like the previous methods reported, and that's how they regenerate. And their network is already doing 93.4%. It's only pre-trained on ImageNet with this inflation concept, but then they also pre-train these models on the kinetics dataset, and then they fine-tune it on these datasets, and then they sort of solve this data problem, and they reach 97.7% of accuracy, and then also 98%. This is fully fine-tuned, and this is just fine-tuned last layer. And yeah, so they're almost reaching like maximum possible of accuracy with this. And another thing they point out is this: why the 3D CNN was not doing that good previously, and why is it going good now? Because you see, for example, looking at the two-stream percentage here, accuracy here, so it goes from, without kinetics pre-training, goes from 91% to 93, but the 3D coordinate jumps all the way from 51% to 76%, and yeah, so that's a big jump. So it probably means that these 3D CNNs are data hungry. Bringing it back. Okay. Yeah, we're close to the end of. I mean, we still have one more paper, but any questions so far? Anybody has anybody worked with this? Active recognition. If you want to add something to it, please feel free. And yeah. So this is another paper. It's called Temporal 3D CNN. So they also drop the optical flow concept again, and they use this. So yeah. So the previous 3D CNNs, they did not exploit this part of having different temporal depths. So the entire network would have the same temporal depth, but they exploit this, and so the their aim is to capture three things, which is the short, medium, and long ranges in a video. Like some things happen over short frames, some things happen over medium number of frames, and some things take like a long set of frames to happen. So they want to capture all of this. So they introduce this thing called a temporal transition layer. So they say that in this original DenseNet there's a transition layer which is just 1 by 1 convolution, and yeah, that's what it is. So they replace that with this temporal transition layer. In the temporal transition layer, you have 3 different convolutions around next to, in parallel, and you have different temporal depths to it. So one would capture short or long or medium ranges, and then you get to bring them together, and you average pool with 3D pooling or something. And yeah, so you've put it in this DenseNet, and in the DenseNet you also have to form it 3D. To do that, they just extend the, what do you say, the kernel's depths across. Just if it's a 3 by 3 kernel, they make it 3 by 3 by 3 in the dense blocks. But just in the in the TTL layer, they introduce this temporal depths, which is different. And yeah, so also to train this model, so they have another way of like transfer learning for this, which is like pre-training somehow, which is okay. So this is their method. They take a normal ImageNet, 2D ImageNet here, and they keep their, I mean, they make a parallel 3D one here, and then So they feed these different images, so either positive or negative pairs. So this one, the blue one, is kind of frozen, and in the end, this overall network is supposed to say is it a matching or not. So if it, let's say we feed it like yeah, so this one will take 64 frames and this one will take like 1 frame, and it could, let's say it's from the same video and predicts it is not from the same video. So it backpropagates these weights to the 3D CNN, and so this one is only helping this one learn. So that's what their concept is. So one learns from the supervision of another, and that's how they transfer learn, like from a 2D coordinate to a 3D coordinate. And yeah, so that's all they introduce. And also their model is just a 3D dense net with these different depths, and they report around yeah, with TSN they report 93.2% accuracy. And yeah, so it's not more than i3D, but for what they complain about is i3D is from DeepMind and they have 64 GPUs to train this model on, and also all of Kinetics dataset, but probably they don't. And another difference is this one, it looks at it takes 64 frames together, and the T3D model, which is a temporal 3D model, it only takes 632. So that could be one of the reasons why it is not doing that. But still, with 94% accuracy, we might not need optimal optical flow here. And yeah, that's all.
So the models which uses optical flow, they pre-compute this optical flow.
Yeah, you have to pre-compute optical flow. There are a lot of like there's a lot of code there. So people say it takes 0.06 milliseconds second to compute like 1 frame. So you cannot do it on the go while training. So you have to do it in the beginning, because one inference takes around 20 frames of optical flow, and if you do batch-wise mini batch training, that also scales up. So that could be a problem. Yeah.
Shubham,
Yes.
in these data sets, it's a single class per video, yes?
No. So I think
single action per video or not?
single action per video, I think, yeah, could be, yeah. And at least UCF and HMDB.
UCF is single action per
It
video.
is, yeah. Kinetic, you think it's not?
I don't know, I'm asking you.
I doubt that, because I didn't look into Kinetic much. It's pretty big to download. I downloaded this, yeah.
Action and activity recognition is two different problems. Action as one action which summarizes the video, and activity you need to pinpoint, for example, enumerate the activities or pinpoint the locations of activities in the video.
Yeah. So this one is mostly action, yeah.
Yeah. So this topic is about action.
Okay.
Action recognition.
Right. So that went off.
I have one more. In most of the tables, accuracies are quite good, and you already mentioned that there's quite a lot of similar classes. So they using the top 1 accuracy or top 3, top 5? How they decide that?
This one, I think it's top 1 accuracy, because some of them they were reporting top 5, and yeah, later they just, I think it's just top 1, just softmax and top whatever predicts the best.
Do temporal and spatial streams carry the same weight, or one of them gives more information about the action than the other?
No, but the spatial stream is supposed to detect objects, so the weights are different. And like, are you saying prediction weights or?
Yes.
In the end, okay. Depends on the model. Some models they weighted by like whatever's doing better, but no, actually no, it's the same weights now. Yeah. Most of the models are same weights. Same weights as in they wouldn't weight it differently. Like one, yeah.
Did anyone try to use sound as well, no? For increasing the accuracy?
You could, but then a lot of, if you apply these models to in the wild, like most of the videos out there, they have really strange sounds happening, because nowadays kids just record something with their drones and put electronic music at the background and don't know what's happening.
for example, in recurrent neural networks,
yeah.
Where the bidirectional models are used, often accuracies are better.
Mm-hmm.
And in those models, if have you seen some results where video is presented in one direction and after that in another direction?
There was this use of bidirectional optical flow though, but that didn't work so well. But no, not so much. Also, I've only seen one or two papers with LSTM, which is one is this one, which I didn't talk about, but they just convert every frame to a feature vector from a WebJet model, and then they feed it to LSTM, and that's all. This how they produce their accuracy. I mean their results. But I doubt seeing anything with the bidirectional flow.
Is there any statistics which model is used most?
Well, every 2-3 months there's a new model coming up, so that one is.
How long it takes to train on such databases?
There was this one paper which specifically says that a 3D CNN takes 2 months to train, which was cited by some other paper. It's like strange thing to see, but I'm not sure.
For single card or?
I'm not sure. I didn't see the hardware thing on that, but I mean the i3D networks, they're trained with 64 GPUs, and I suppose it does take long. But also depends on which data set are you training on.
Thanks for the presentation.
Oh, thank you.
Shubham.
Yeah.
Have you do this in the these latest networks? Do they resemble the videos or not? No, the content frame rate or not? Or they use
25 frames per second.
25 frames.
Yeah, most of, I mean that's what 15 done, and then
Because
everybody
for CNN you need to fix the length like frame input, yeah.
That input. Okay.
Yeah. For example, your video is like two minutes, yeah.
So are you talking about RGB ones, or are you talking about?
Yeah, but like this 3D convolutional.
Okay.
Yeah. So for example, this somehow because you need to resample them.
Yeah. So there's 16 frames, there's 32 frames, and there's 64 frames. So in the i3D paper, they go all the way to 64, but the T3D one, they try 64 and 32, but 32 works better, they say.
So they just take first 64 frames, then like bestride one, another 64, or just just to convert the video to 64 frames.
No. They just,
I need to read the paper.
Right. But they sample like directly any random 64 frames from the video, and based on the motion happening in that they predict. Yeah.
Okay, I got it. That's very nice.
Question
Yeah.
about last page of your
Yeah. I can open it. Yeah. Okay. I might have closed it, but let's see.
Switching to refreshment. Yeah.
Box.
Oh yeah.
Yeah, this one. Yes.
This one. You have a somehow 2,000 of features here, and then you get a decision.
Yeah.
0 or
Right. So this one and this, right?
Yes.
Are you saying 128 to 0 and 1?
Yes.
So I think it's like binary classifier here.
It's like Siamese network, Alexander. It's like Siamese network. In face recognition, we use, for example, they put two images, and then you say yes, it's same or not same. It's the same concept. It's Siamese network.
Siamese.
Yeah,
Just here,
the
this
same
one is
concept,
frozen.
I think.
Yeah. So.
Okay.
But this green network is initialized from ImageNet or just randomly?
It is no. It starts with random weights actually
randomly
because
and then pre-trained in this manner, yeah?
So
Yeah.
these features are trained in the same iteration with the Siamese network, or they are trained separately.
So this one is a 2D network which is already trained, and this one is initialized on the spot, like 0 from scratch.
But
So yeah.
what is actually okay? Blue one is trained, then the 0 trained, and after all the red one is trained. Yes.
Oh no. What happens is so you feed in the same things like one image from this video and like 64 or 32 frames from the same video, and then they predict something and they're supposed to predict is it right, wrong or right. So in case they predict something wrong and then they backpropagate, they only go into this network backpropagation. This one is frozen.
Red and
Yeah.
and green are trained at the same time.
Yeah, so the green is actually trained, and yeah, I mean the red we can just throw away later, and only uses 1024 network thing.
Okay,
Yeah,
clear. Thank you.
no problems.
Javas gal yra kas nors tiesiog
Niekas spėjų nenaudoja.
naudoja viską. Naudoja MATLABą, ta prasme, čia priklauso nuo kas tenai, kas kokį softą turi. Kiekviena kompanija, ta prasme, tenai, koks nors Intelis turi savo frameworką, tenai, Categorizing, tenai, Facebookas, tenai. Kiekviena kompanija daro savo custom framework. Ir garantuoja, kadangi mes neprogramuojam, tai garantuoja, kad ir su Java yra. Prasme, jokio skirtumo, ir su Sharp gali rašyti.